All right, so today we're talking about functions, specifically linear functions. We'll dive into what functions are later on this week, but today we're really going to look at linear versus nonlinear patterns. So to start, you might recognize these two words. We have dependent variables and independent variables. And you might know those words actually from science class, because what you might remember is independent variables are things that we can change or manipulate or have control over, and they will impact my dependent variable, okay? We also call independent variables our inputs, right? Because we can change what we put into like a machine, but then what it outputs for us isn't up to us, right? That's what the pattern the machine will do. In math, independent variables are always going to be our x value, and our dependent variables are always going to be our y value, okay? All right, so let's just look at this first problem. So if I just look at the picture alone, we're trying to find perimeter, okay? So perimeter, remember, is the sum of all my sides. So I know that a rectangle, its opposite sides are the same. So if I were to add up these sides, I would have 6 plus 1 plus 6 plus 1. I would get 14. So that's my perimeter. Let's try with the next one. Okay, so again, I have these two side lengths I know, so I would add these up. I get 12, 13, 14, 15, 16. I would have 16. Okay, the next one, we would get 18. And the last one, if we add those up, we would get 20. Okay, so you might already kind of notice a pattern here, but if not, that's okay. We'll name it specifically in a minute. All right, so let's just fill in this chart. One way that we can show relationships is through pictures like we saw up there, but the most common way we show patterns is through a table. So here we have our independent variable. It's our x values, right? The number of rectangles. Okay, we've got 1, 2, 3, 4 rectangles. And then we found perimeter by adding up their sides. So for example, for the first one, we did 6 plus 6 plus 1 plus 1, and we got 14. Okay. Then we added up the next one. We got 16, then 18, then 20. Okay. Now we can write our values in a chart as an ordered pair. So if you look up here, it's kind of giving me the framework for it. My ordered pair always has my independent, my input, or my x value first, and my dependent, my output, or my y value last. So we're going to write these all as points. And when I write this as a point, I'm going to take my independent variable, and that's my x value. And then when I plugged that independent variable in, I got the dependent variable of 14. Okay, so that would be my point, 1, 14. Same with the next one. Okay, my independent variable is 2, so I'd have a 2. Comma, my dependent variable was 16, so I would have 16, okay? And we would go on from there. So my independent variable is 3, my dependent variable is 18, my independent variable was 4, my dependent variable was 20, okay? Now, because we're able to write these as a point, we're able to graph them, okay? So we're going to skip step 2. We'll come there next. Let's just graph these as points. So our first point was 1, 14. So I'm going to come down here. I'm going to go 1 up to 14. I'm going to have to eyeball a little bit here. We were like right there, okay? All right, my second point was 2, 16. So I'm going to put a point at 2, 16. 3, 18. And then 4, 20. And if you notice these dots, you'll notice that they're forming a pretty straight line, okay? So if I were to connect them, I could make it here, okay? And it connects on a straight line. All right, so now when it says look for a pattern, it's really just talking about an equation, okay? When we write an equation, we always start with our dependent variable y equals, and then we're going to have something related to x, right? There's a relationship between my independent, my dependent variable. Okay, now here's the pieces on how we write this. The first part, the number that's right in front of my x, this is probably the most important part. We're going to spend chapters on figuring out this number and what this number means, okay? But a little fraction that I like to use that helps me, and this is actually college math, so you guys can now go home and tell all your people that you know college math. But we like to call it change in y over change in x. Those little triangles mean change in, okay? So a change in y over a change in x. And it's exactly what it sounds like. So let's come up to our table. What is our change in y? Well, how's my y changing? How do I go from one y to the next? Going up 2, going up 2 again, and I'm going up 2 again, okay? So notice I'm going up by the same numbers. And over here, my change in x is, I'm going up by 1, going up by 1, going up by 1. Great, okay? So notice all my changes are the same, right? We're going up by 2 every time. We're going up by 1 every time. So if I were to write this in our fraction, my change in y would be 2 because I'm going up 2. And my change in x would be 1 because I'm going up 1. Okay? That's how we write that number. And basically all we're saying is 2 times my independent variable gives me my dependent variable. Let's test that. So if I plug my independent variable 1 down here for x, in other words, I'm doing 2 times 1. Okay, I just plugged my independent variable in. Plugged my 1 in for x. If I do that, I have 2 times 1. Well, I get 2, but what do I wish I got? 14. My goal is to get a 14, so what would I need to add in order to get 14? I would need to add 12. So let's add a plus 12 to my pattern. And there's my equation, okay? Now, let's look at our graph. We see this also down here. If you would, this would be my starting point, okay? This is where I'm starting. If you look at where we start, we're at 12, okay? So we're starting this phase of writing our equations for graphs. All right, so go ahead and copy these two down. Like I said, we're going to be focusing on functions later this week, so put a little star by that. We'll hit that later on. We'll really spend a whole day talking about what it means to be a function and a not a function. Today, we're going to focus on linear functions, okay? Linear functions are functions whose graph is a non-vertical line or part of a non-vertical line, okay? So, for example, let's look at our table, okay? So when we look at our table, we're going to be finding our change in y. Okay, so as I look at this, I'm going down 3, then I go down 3 again, and then I go down 3 again. On the x direction, I'm going up 1, going up 1, going up 1. Okay, so in other words, if I were to be thinking about this as terms of my relationship, again, I like to think of the change in y or change in x to help me here. How is my y changing? Well, I'm going down 3 megabytes for every 1 photo. Okay, so where did I get all those pieces? Well, I got my down 3 megabytes from right here, going down 3. For every 1 photo, I got from right here, okay? So that's how we would describe it. All right, let's write an equation. So here's my y equals, okay, my change in y is -3 over 1. I've got my x. And then what's my starting point? Well, fine, if you have a 0 in your chart, that's perfect. That's 0, the matching y is my starting point. So you don't have to do any math there. Okay, it's just given to us in the table. All right, so now the question of, is this relationship linear? So I have it graphed over here to the side. I notice it's a perfectly straight line. Also up here, I notice that my change in y is the same. If my change in y is the same, assuming this is the same as well, if this is the same and it's a straight line, then yes, this is linear. All right, go ahead, try A and B. All right, so for A, we should have got that it was linear, and here's the equation that proves it, right? We have our change in y was 2 over our change in x, which was 1. x plus 8 because 8 is with the 0. Okay, right here. So I know it's plus 8. Okay, the bottom one, drawing a table is what helps you solve this one. If you draw a table and fill it in, you'd notice pretty quickly that it's nonlinear, right? Because I'm changing by different values. And I actually see 2 1s here. We'll talk about this later, but this isn't even a function, okay, because of that. All right, so we have linear functions, nonlinear functions. All you really need to know is linear functions are straight lines, and the change in y is always the same for linear. Okay, so straight line, same change in y. Okay, and these are just some examples of different graphs that would show me a linear versus a nonlinear function. All right, so if I look at this graph right here, we're talking about area and of pizza, cost in dollars, and we're talking about sauce. Okay, so for our first one, we're talking about pizza area. Okay, so here's the radius and the area. If I were to plot these points, so the first one's plotted for us. The second one, 4, go up to 50, I'm about here. Oh, right above that one, yep. 6, I go to 113, so I'm about here. 8, I'm going to 201, so I'm a little bit above that. And 10, I'm going to 314. So if you look at this graph, we will notice it's not straight. In fact, there's a very slight curve happening. Okay, we're kind of curving up, if you will. Okay, so this would be a non-linear example. And if you were to test this over here, you would find that our changes in y's are different values as well. Okay, both of which would prove nonlinear. Look at our sauce. Okay, so let's graph this one. So the first one, we're going to eyeball this, but we have 2.80 cents, so I'm not quite at $1. Then we have 4, and we're at 160, so I'm about a little above halfway. 6 to 40, so I'm about halfway again. 8, I'm at 320, so I'm about right here. And 10, I am at 4 even. So if I look at this graph, it's looking pretty straight to me, okay? It's looking pretty straight to me, okay? However, because I had to eyeball it, I'm not super confident that this is linear yet. So let's just test this. I have 160 minus 80. We're going up by 80 cents. Let's check the next one. Now it's also up by 80. And you'll quickly find that each of them are up by 0.80. So this is linear. All right, on the back, we have some very special cases. So on the back here, notice our chart. We're talking about a Rubik's Cube, pretty much the blocks of a cube. We're given the independent is the number of blocks on the edge. Tells me there's a relationship between the total number of blocks on my cube. Now, if you sit here and notice, we go up 7, and then we make a huge jump. We go up, what would this be? 19, I think. Yeah, 19. Okay, we go up 19. So right away, we know it's nonlinear. But that doesn't mean there's not a relationship, okay? We just know it's not a linear one, okay? If you noticed anything about how I go from 1 to 1, or 2 to 8, or 3 to 7, okay? If you're thinking to yourself, oh, you could just cube this, and it would give us our answer, you are absolutely right. If we take the cube of our independent variable, we would get our dependent variable. Okay, so in other words, to almost think about this in terms of like a description, like what's going on in words, we would say the number of blocks is the cube of the number of blocks on the edge. Okay, as an equation, we would say y equals x cubed, right? Here's our independent variable. We're cubing it. That gives us our dependent variable. Okay, and for time's sake, I'll just give you our graph. It would look something like this, something like a U going up. All right, look at our next one. Okay, here's our chart giving us our relationships here between our numbers. And this one's challenging. It's hard to see. Okay, but again, if you notice here, we're not adding the same number, so we're not doing +6 every time. That doesn't work. Okay. However, what you might notice is I'm multiplying by 3. So in other words, I'm doing 3 times 3 to get 9, and then I do 9 times 3 to get 27. Okay, so that's one thing I might notice. Let's look at our picture. So on our picture, we have one branch that breaks into 3. Oh my. Breaks into 3. Then we have our 3 branches from before break into 3 more. Okay? Then we have our 3 branches from before break into 3 more. Okay? I'm not going to be able to draw it now, but we see just this continual branching. Okay? So in other words, in words, we would say in each figure, you are splitting 3 more branches. Okay? And our equation is very hard to tell, but we're going to do y equals 3 raised to the x. Okay? And that would tell me how many branches we have. Okay, and my graph would look just like a U again. It'd just be a lot steeper. Okay?